Oh, did I get started? Yeah. Okay, so my name is Sagar. I'm from the University of Waterloo. And today I'll be presenting human-inspired whole-body stabilization on balance boards for humanoid robots. This is some preliminary work in our lab. So balancing and stabilization is important in unknown and dynamic environments. It's challenging and generally requires specialized control approaches. So, for example, in the future, if humanoids are using other personal transporters, but also if they're maybe riding buses or, on boats. I don't know about you, but a humanoid bringing me a beer on a yacht is my ultimate goal. But yeah, so this is to kind of motivate the problem further. But in this work, we kind of investigate human and humanoid balancing on passive and active balance boards in the sagittal plane. For the humanoid, so far we've kind of worked on actuated balance boards, so where we power it externally. Ultimately, we want to move towards a passive balance board. So, from some motion capture trials, I'll just say some qualitative analysis here, but humans keep both feet fixed on the board and their torso kind of upright. Humans let their ankles be compliant to the board's motion and can also command a torque on the board. And so using these, we can synthesize kind of similar strategies for humanoids. So this is our overall block diagram of the controller. The first part is kind of like a stabilizer, generating task-based references for the center of mass, feet, upper body, etc. The next is kind of like the whole body QP, doing task-based inverse dynamics. And finally, the output is sent to our robot. It's the ReamZ made by the wonderful folks at PAL Robotics. And so I'll start first with kind of this stabilizer block diagram. So one strategy we use is kind of this ankle strategy. So the idea here is just to kind of command ankle roll and pitch correction. So you can see if we have some kind of reference COP, then the robot can kind of conform to the tilting of the board. We do take into account some a priori knowledge of the balance board geometry here to estimate the contact point on the ground. But in our hardware experiments, we did not have this. So next is kind of this center of mass admittance. So here we kind of take into account a bit of the unmodeled flexibility in the ankle. So this system is basically the table cart model with a small spring at the pivot point, and so we linearize the system and apply LQR to generate this strategy. And so this is just some basic push recovery behavior here. The next is kind of base orientation admittance or foot force difference control. So the idea here is to roll the base and kind of even out the forces between the feet. And so that's the idea here. And finally, we have this kind of base pitch admittance. So we're trying to keep the base upright. So even with just the ankle strategy, sometimes we might tilt and fall over because the base is kind of back. So it's kind of an important stabilization strategy. So that's basically the stabilizer. I skipped two parts here for sake of time, which is the angular momentum regulation, or trying to keep that at 0, and the contact wrench distribution. But I do have a poster later as well. So next, I'll quickly go over this TSID block. So this is kind of like the high-level overview. So this is kind of a whole body QP. It just sums task functions into a general cost function using user-defined weights and priorities. So the different tasks we impose for our work are listed here. And these are taking inputs from the stabilizer as task-based references. So I've covered these two blocks. The next is just double integration because we get out joint accelerations from TSID. And then we send these to the robot. So this is one simulation trial here. There will be some graphs that pop up, but they might be hard to read. But here the board is tilting and the robot is compensating. There's also a push that occurs here. The arms kind of swing back to stabilize. And then, oh, sorry. One second.
This is a motion capture replay?
No, this is a simulation trial in like a simulator, a physics simulator. Sorry, I do have a hardware trial here. Okay, let this play. So yeah, this is a physics simulator, and there's a push here. Okay, yeah, so this is a hardware trial. We are going a bit slower on hardware. We do have some work to do for our state estimation and things, but again here, when we apply push, the robot is able to compensate, and all the strategies are at play here. And also here is just a sped up version to kind of see that all the strategies are working. Our hope is to go much faster in real life, and I'm getting that years. So we're also trying this in different planes. Again, ultimately we want to move to a fully passive board to test this for the humanoid. And maybe 3D balance boards. Okay, so this is a summary of what we presented so far of our preliminary work. Some future steps are, for example, to look at actually generating angular momentum references and potentially using like a whole body strategy or full body MPC. Okay, thank you very much for your attention.
So is the robot anywhere aware of the curvature of the balance board? Is it all just naively being like for sure?
Oh, yeah, so in simulation we did take into account the curvature, but because we attached like an IMU to the board, but in real life, no. It's just like a perturbation. So we try to keep the center of pressure at the center of the
So it's part of, so it's aware that like, so it knows with the simulation that it's a certain radius of curvature.
Yes, correct, yeah.
So have you checked what happens if your feet are not exactly in parallel?
Oh yeah, that's a good question. No. But I think we will try to do that as well, and I think the strategy should maybe compensate for small variations, but I think that is an interesting point, which I haven't checked.
Okay, thanks.
Yep.
A closely related question. In sim, have you tried doing this with a uncertainty in the robot's center mass?
Oh, not yet, but that is also a good point. I think in simulation we'll try to add like a lot of like noise as well to kind of
It's
simulate.
not noise.
Or okay.
So we've tried stuff with like bouncing on a line contact in other
Oh.
contexts,
Mm-hmm.
and you basically have to estimate the CG online.
Oh, I see.
On
Okay.
hardware. You can't know it well enough because you have to keep the CG over that line, right? And it has no volume or area, so there's no, it's a little annoying.
Okay. Yeah. It's something we'll consider. Oh, yeah. Sorry.
Sort of two slightly related thoughts. If you take the curve in the bottom and just make it progressively flatter and flatter, there's a continuum all the way from a flat ground to point foot, which your curve thing is, with your ball is halfway through that. But you can balance all of them as the motion of the upper body, the motion of the center of mass is primarily dictated by where is the center of pressure compared to where the center of mass is. And that's true for the flat foot as well as for the flat foot. So it seems like you could just have the same control strategy on these on this curved board as you do for the flat foot, which is just, you just corral the center of mass by moving the center of pressure outside the center of mass. And then with your curved foot, you just say, where do you want the contact point to be? And all your ankle torques and all that are just towards the end of moving the contact point to the same place you would have put it with the flat foot robot.
Yes.
So it's not really, doesn't have to be thought of as a different task. Is that crazy what I said, or right or wrong, or?
I think that's in general probably correct, because this type of stabilizer type of design is actually used a lot in walking stabilizers as well on flat boards. So I think that makes sense. So I think intelligently placing the contact stabilizes this.